Picture this. You're trying to open a file on your computer, but it feels like it's taking so long. You wonder, why is this so slow? Behind the scenes, your computer's operating system is juggling multiple requests to read and write data from the disk. The speed at which it does this depends on something most of us don't think about: disk scheduling algorithms. These algorithms determine the order in which your data is accessed, and the difference between a good algorithm and a bad one could mean the difference between instant access and frustrating delays. Today, we will discuss disk scheduling and explain how it works and show why it's essential for your system's performance. Disk scheduling, also known as input-output scheduling, is the technique operating systems use to determine the order in which disk input-output requests are processed. Its primary goals are to 1. Minimize seek time, 2. Maximize throughput, 3. Minimize latency, 4. Ensure fairness, and 5. Optimize resource utilization. These algorithms significantly impact the efficiency of data access and consequently the system's performance. Let's explore key terms before proceeding deeper into specific algorithms. First is the seek time. It is the time taken for the disk arm to reach the desired track. Next is the rotational latency, the time for the desired disk sector to align with the read-write head. Transfer time, the time required to transfer data, depending on the disk speed and data size. Then, we have the disk access time, which is the sum of seek time, rotational latency, and transfer time. We also have the disk response time. It is the time wherein a request waits before being processed. Understanding these terms helps us evaluate the efficiency of different disk scheduling algorithms. There are 6 primary disk scheduling algorithms. First come, first serve, shortest seek time first, the scan algorithm, the circular scan algorithm, look algorithm, the circular look algorithm. Each algorithm has its unique approach to organizing disk requests. Let's go through them along with some examples. Number 1. First come, first serve. First come, first serve processes requests in the order they arrive. For example, with requests at 82, 170, 43, 140, 24, 16, and 190 starting at pointer 50, the total head movement is 642 tracks. Its advantages are that it can be simple and fair and no requests for starvation. On the other hand, its disadvantages are it does not optimize seek time, which may also lead to longer wait times. Next, we have shortest seek time first. This prioritizes requests closest to the current head position. For example, using the same requests and starting at 50. Shortest seek time first reduces head movement to 208 tracks. It has faster response times and improved throughput. However, it can cause starvation for distant requests and has a high variance in response times. Next is scan. Scan moves the disk arm in one direction, servicing requests and then reverses direction. For instance, for requests at 82, 170, 43, 140, 24, 16, and 190, starting at 50 and moving upwards, the total movement is 332 tracks. It has a high throughput as an advantage and a balanced response time, but longer wait times for requests just serviced or the locations on the disk that have been recently accessed or processed by the read-write head. C-scan, on the other hand, improves scan by moving the arm in one direction only, wrapping around to the start without reversing. Example, the total movement becomes 391 tracks. It has uniform wait times and a better response time, but it increases seek movements. The look algorithm works like scan but reverses direction at the last request instead of the disk's edge. For example, suppose the disk requests are 82, 170, 43, 140, 24, 16, and 190, and the read-write head is initially at 50. In the look algorithm, the disk arm moves in one direction, servicing requests until it reaches the furthest request in that direction. Then, it reverses, only servicing requests requests in the path. Unlike scan, it does not travel to the physical end of the disk if there are no requests there. The total head movement is 314 tracks. It reduces unnecessary traversal, which also improves its performance over scan. Unfortunately, there is an overhead of finding the end request. Circular look or C-look builds on look, moving to the farthest request in one direction and directly wrapping to the nearest request at the other end. The total movement is 341 tracks. The advantages are the better performance that it has than look and reduced wait times for recently visited requests. Disk scheduling algorithms like first come first serve, shortest seek time first, scan, C-scan, look, and C-look play a very important role in optimizing system performance. The choice of algorithm depends on the system's needs, balancing seek time, throughput, latency, and fairness. By understanding these algorithms, we can implement solutions that ensure efficient, reliable, and faster data retrieval in our systems.